Okay, to round out the week, we are going to do a rapid-fire set of misconception questions. Go to the first one, misconception question number 1. It says the figure shows 3 arrangements of electric field lines. In each arrangement, a proton is released from rest to point A and is then accelerated through point B by the electric field. Points A and B have equal separation in the 3 arrangements. Rank their arrangements according to the linear momentum of the proton at point B. Greatest first. Okay, the first thing you need to think about is the momentum will be greater if the electric field is greater. Because remember, the acceleration that a particle experiences is equal to E times Q over M. We learned that earlier in the chapter, right? So wherever you have the biggest average electric field, you have the biggest average acceleration. If you have the biggest average acceleration, you have the biggest average velocity. If you have the biggest average velocity, you have the biggest average momentum. Make sense? Thought so. Okay, so now, where in these 3 pictures do you have the greatest? So I'll just say really quick. We have A looks like this. B looks like this. And C looks like this. So this is A, B, and C. In which of these 3 pictures do you have the greatest average electric field so that we have the greatest, biggest acceleration? Well, where the electric field lines are closest. And we see that on average, they're closest at A, so that has to be the biggest. They're the second closest on average at B, so A is bigger than B. But B, you still have this part that's closer, which is closer than this part of C, so B still has to be bigger than C. So the correct answer would be A must be bigger than B, must be bigger than C. Awesomeness. All right, let's move on to the second one. Misconception question number 2. It says the figure shows 4 situations in which 4 charged particles are evenly spaced to the left and right of a central point. The charge values are indicated. Rank the situations according to the magnitude of the electric field at the central point, greatest first. So we don't care about what direction the electric field is. We care about the magnitude. So just how big is it, all right? So I'm going to draw each of these situations. So here's going to be my middle point 1, my middle point 2, my middle point 3, my middle point 4. And so on this side here, we have a negative E here. We have a positive E there. We have a negative E here and a positive E there. Okay, this is going to be positive E, negative E, negative E. This is going to be a negative E, positive E, positive E, positive E. And this is going to be negative E, positive E, negative E. Okay, all right. First things first. Any of these that are totally symmetrical, right, are going to cancel out and there's going to be no electric field, right? So for example, option 1 here, so this is 1, 2, 3, and 4. Option 1 here is totally symmetric. You have close by 2 negatives, far away 2 positives. We know here the electric field must be 0. Okay, so that's probably going to be the least, right? For the rest of these, I'm going to go ahead and draw vectors that represent the electric field due to the various particles. Okay, so the ones close by, they're going to get a bigger vector, and the ones near or the ones far away are going to get a smaller vector because electric field gets smaller as you get farther away as R gets bigger. So this particle here will create a small electric field in this direction. This charge here will create a big electric field in this direction. This electric field here is negative, right? So electric fields point towards negative particles. That'll be a big electric field towards this particle. And over here, you're going to have another small electric field pointing towards it because they're farther away. Okay, so in this case, you have all these electric field lines pointing in the same direction. This, too, is a contender to be the biggest. All right. Now, this negative electric field is going to create this negative charge is going to create an electric field pointing this way, but small because it's farther away. This positive charge is going to create an electric field in this direction, but big. Okay. this positive charge here is going to create an electric field in this direction, big, because it's pointing away from positive charges. And this positive charge here is going to create an electric field in this direction that's small. Okay? So what do we see here? We see this cancels out with this, and we're left with 2 small in this direction. So this one, number 2, has to be bigger than number 3, because you only have a net electric field of 2 pointing in the negative direction. All right, let's look at the last one. We have a big electric field pointing in this direction due to this charge, a small electric field in this direction due to this charge, and another big electric field pointing in this direction due to this charge, because it's positive and it's close. And then you have a small electric field pointing towards this charged particle over here because it's negative. All right, these 2 will cancel, right? And so now you have 2 bigs pointing in the negative direction. So this is what I get. I get that 2 must be the greatest. And that then is the next biggest one's going to be 4, because that's 2 positives in this direction. Remember, the direction doesn't matter, it's just magnitude. And that's going to be bigger than 3, which has 2 smalls pointing in this direction, which has to be bigger than 1, which is nothing at all, no electric field at all. And that will be how we sort the electric field due to these. The purpose of this misconception question is to really just, get a intuition for how electric fields add due to charged particles in different positions. Luckily, this question was nice enough not to put things at angles, so you didn't have to do any sines or cosines. Okay, last one, misconception question 3. It says, 5 protons are launched in a uniform electric field. Rank the protons according to the magnitude of their accelerations due to the field. Greatest first. Okay, so here's a trick question. You have same electric field in all of space. The only difference is the particles are moving in different directions. Ladies and gentlemen, that does not matter whatsoever. The direction that the charged particles are moving or what their velocities are does not determine the magnitude of the acceleration. Remember, the magnitude of the acceleration is only determined by this one equation. Acceleration equals EQ over the mass. So if E is constant, they're all the same charge and they're all the same mass. The acceleration will be the same for each. We did not let this question trick us, and for that, I'm very proud of us.